So what is an energy eigenstate? Well, it's a solution of this equation. So a solution psi, a solution for psi is an energy eigenstate. Then the set of values of E is the spectrum. And if two values of E correspond, if there is a value of E that has more than one solution, we say the spectrum is degenerate. So a degenerate spectrum is more than one psi for a given E. So these are just definitions, but they're used all the time. So our energy eigenstates are the solutions of this. The funny thing about this equation is that sometimes the requirement that psi be normalized means that you cannot always find a solution for any value of E. So only specific values of E's are allowed. You know that for the harmonic oscillator, for example. And therefore, there's something called the spectrum, which is the allowed values. And many times you have degeneracies, and that makes for very interesting physics. So let's say a couple more things about the nature of this wave function. So what kind of potentials do we allow? We will allow potentials that can fail to be bounded. What do we allow? We allow failure of continuity. Certainly, we must allow that in our potentials that we consider, because you have even the finite square well. The potential is not continuous. You can allow as well failure to be bounded. So what is a typical example? The harmonic oscillator, the x squared potential, is not bounded. It goes to infinity. So we can fail to be continuous, but it can fail at one point, another point, but it shouldn't fail at infinitely many points, presumably. So it's piecewise continuous. It can fail to be bounded, and it can include delta functions, which is pretty interesting, because a lot of physics with these delta functions, but a delta function is a complicated thing. We'll include delta functions, but not derivatives of them, nor powers. So we won't take anything more strange than delta functions, collections of delta functions. So this is really how delicate your potentials will be. They will not be more complicated than that, but for that, we will assume, and it will be completely consistent to require the following for the wave function. So psi is continuous, psi of x is continuous and bounded, and its derivative is bounded. Psi prime is bounded. I will not impose any condition that is further than that, except the condition that it be normalizable. So, and even that we will be a little, how would I say, not too demanding on that, because there will be wave functions like momentum eigenstates that can't be normalized. So we'll leave it at that. I think probably this is what you should really box, because for a momentum eigenstate, e to the I px over h bar, this is a momentum eigenstate. This is continuous. It's bounded. The derivative is bounded. It's not normalizable, but it's so useful that we must include it in the list of things that we allow. So bound states and non-bound states are things that are not normalizable. So I don't put normalization. Now, if you put normalization, then the wave function will go to 0 at infinity. And that's all you would want to impose, nothing else. So really, in some sense, this is it. You don't want more than that. Now I want to say a couple of things about properties of the eigenstates. Now, we will calculate many of these eigenstates, but we need to understand some of the basic properties that they have. And there's really two types of identities that I want you to be very aware that they play some sort of dual role, and an interesting dual role, and has to do with this wave function. So the eigenstates of H hat, these are the energy eigenstates. You can consider them and have them make a list of them. So you have an energy E0 less than or equal than E1, E2 just goes like that, and you have a psi 0, psi 1, all these wave functions, and then H hat psi n is equal to En psi n. You have a set of solutions. So this is what will happen if you have a good problem, a reasonable potential, and nothing terribly strange going on. There will be a lot of solutions, and they can be chosen to be orthonormal. Now, at first sight, it's a funny term to use, orthonormal. This is a term that we use for vectors. Two vectors are orthogonal, and we say they're orthonormal if they have unit length and this like that. But what do we mean that two functions are orthonormal? Well, are functions vectors? Well, that's a little dubious, but the way we will think in quantum mechanics is that in some sense, functions are vectors in an infinite dimensional space. So just vectors, but not in 3 dimensions. Why? Think of it. If you have a function, you have to give values, independent values at many points, infinitely many. And if you give all those values, you got the function. If you have a vector, you have to give components, and you got the vector. So in a sense, to give a function, I have to give a lot of numbers, and I can say the first vector is the value along the direction. The first component is the value around 0. The second unit vector is the value about 0.01, 0.02, go on, and then list all of them, and you have a vector of infinite dimensions. You'll say, totally useless. No, it's not totally useless. It's actually, if you visualize that, and we'll do it later more, you will be able to understand many formulas as natural extensions. So what does it mean that these two functions are orthonormal? Well, a dot product or an orthonormality is to say that the dot product is 0. And the way we dot product two functions, psi m and psi n of x, is we take their values at the same point, we star 1, and we integrate. And if this is equal to delta mn, we say the functions are orthonormal. Normal. So ortho for orthogonal, which says that if m is different from n, the Kronecker delta, that symbol that is equal to 1 if the two labels are the same or 0 otherwise, if they're different, you get 0. The inner product, this left-hand side is called the inner product, is 0. On the other hand, if they are the same, if m is equal to n, it says that the integral of psi squared is 1, kind of like a wave function that is well normalized. So we say normal for orthonormal. So these are orthonormal wave functions, and that's good. This is called orthonormality. But then there's a more subtle property, which is that this set of functions is enough to expand any function in this interval that you're doing your quantum mechanics. So if you have any reasonable function, can be written as a superposition of these ones. So this differential equation furnishes for you a collection of functions that are very useful. So this is orthonormality. There's also completeness, which is to say that any function can be written as a sum of this function. So I will write it as this. Psi of x, an arbitrary psi of x, can be written as Bn psi n of x, n equals 0 to infinity, where the Bn's are complex. So this is an assumption, but it's a very solid assumption. When you study differential equations of this type, Sturm-Liouville problem, this is one thing that mathematicians prove for you, and it's not all that easy. But the collection of wave functions is good in this sense. It provides you a complete set of things that any function can be written in terms of that. I'm not saying this satisfies any particular equation. You see, this function satisfies very peculiar equations. There are those equations, but this is an arbitrary function. And it can be written as a sum of this. Since these equations have different energies for different psi's, this psi here satisfies no obvious equation. But here is the problem that this is useful for. Suppose you're given a wave function that at a given time, you know what it looks like. So here is your wave function, psi, and you know that psi at x and time equals 0 happens to be equal to this psi of x that we wrote above. So it's equal to Bn psi n of x. Well, if you know that, if you can calculate these coefficients, that is, you have the wave function at time equals 0 is known, say, and it's given by this thing, which is then written in this form. If you can write it in this form, you've solved the problem of time evolution, because then psi of x at any time is just simply obtained by evolving each component, which is Bn e to the minus I E n t over h bar psi n of x. So this is the important result. Now look what has happened. We replaced each term, we added this exponential. Why? Because then each one of this is a solution of the full Schrödinger equation. And therefore, a superposition with complex coefficients is still a solution of the Schrödinger equation. Therefore, this thing, I've put by hand this, you would say it's ad hoc. No, It's not. We've put it by hand, yes, but we've produced a solution of the Schrödinger equation, which has another virtue. When t is equal to 0, it becomes what you know the wave function is. So since this solves the Schrödinger equation, and at time equals 0 gives you the right answer, and you remember that the Schrödinger equation, if you know it at time equals 0, determines the wave function everywhere, this is the solution. It's not just a solution, it's the solution. So you've solved this equation, and it's a very nice thing. It all depends, of course, on having found the coefficients Bn. Because typically, at time equals 0, you may know what the wave function is, but you may not know how to write it in terms of these coefficients Bn. So what do you do then? If you don't know those coefficients, you can calculate them. How do you calculate them? Well, you use the orthonormality. So you actually take this and integrate against another psi star. So you take a psi star sub m and integrate, multiply and integrate. And then the right-hand side will get a Kronecker delta that will pick out one term. So I'm just saying in words a two-line calculation that you should do if you don't see this as obvious, because it's a kind of calculation that you do a few times in life, then it becomes obvious and you never do it again. And it's minus infinity to infinity dx psi m star of x psi of x dx. So Bm is given by this quantity, or Bn is given by this quantity. You obtain it from here plus orthonormality. So once you have this Bn, you can do something that may, you look at these things and you say, well, I'm bored, what should I do? You say, well, you have Bn, plug it back. What happens then? And you say, why would I plug it back? I don't need to plug it back, and that's true, but it's not a crazy thing to do, because it somehow must lead to some identity, because you solve an equation and then plug it back and try to see if somehow it makes sense. So either it makes sense or you learn something new. So we were supposed to calculate the Bn's, and now we have them, so I can plug this back here. So what do I get? Psi of x now is equal to the sum from n equals 0 to infinity, Bn, but this Bn is the integral of psi n star of x prime. I put here psi of x prime, dx prime. I don't want to confuse the x's with x prime, so I should put x primes all over here. Psi n of x. Well, can I do the integral? No. So have I gained anything? Well, you've gained something if you sort of write it in a way that psi is equal to something times psi. That doesn't look all that simple, but we can at least organize it. Let's assume things are convergent enough that you can change orders of sums and integrals. That's an assumption we always do. I'll write like this, the dx prime, and now I'll put the sum here, equals 0 to infinity of psi n star of x prime, and I'll put the other psi here as well, the psi n of x over here. I'll put a parenthesis, and finally the psi of x prime here. So now it's put in a nice way. And it's a nice way because it allows you to learn something new and interesting about this. And what is that? That this must be very peculiar function, such that integrated against psi gives you psi. And what could it be? This is of the form, if you wish, dx prime, some function of x and x prime, times psi of x prime. So this k is this thing. Well, you can try to think what this is. If you put a delta function here, which may be a little bit of a cheat, you will figure out the right answer. This must be a function that sort of picks out the value of the function at x by integrating. So it only cares about the value at x. So it must be a delta function. So in fact, this is a delta function, or should be a delta function. And therefore, the claim is that we now have a very curious identity that looks as follows. It looks like n equals 0 to infinity, psi n star of x prime, psi n of x, is actually delta of x minus x prime. So this must be true. If what we said at the beginning is true, that you can expand any function in terms of the eigenfunctions, then, that's not such a trivial assumption, and therefore it allows you to prove something fairly surprising. That this must be true, that this identity must be true. And I want you to realize and compare and contrast with this identity here. One is completeness, one is orthonormality. There are two kinds of sums going on here. Here you sum over space, and you keep labels arbitrary, label indices here arbitrary. So you sum over space. These functions depend on space and on labels. You sum over space and keep the labels, and you get sort of a unit matrix in this space, in the space of labels. Here, you keep the positions arbitrary, but sum over labels. And now you get like a unit matrix in the space of positions. Something is 1, but actually infinite, but you could do better when x is equal to x prime. So if you think of it as a matrix, this function in x and x prime, it's a very strange matrix with two indices, x and x prime. And when x is different from x prime is 0, but when x is equal to x prime is 1, but it has to be a delta function because continuous variable. But it's the same idea. So actually, if you think of these two things, x and m, as dual variables, this is a matrix variable, and then you're sort of keeping these two indices open and summing over the other index, multiplying in one way, you get a unit matrix. Here, you do the other way around. You have a matrix in m and n, and this is a more familiar matrix, but then you sum over the other things. So very dual, and two properties that look very different in the way you express them in words. One is that they're orthonormal. The other is that they're complete. And then suddenly the mathematics tells you that there's a nice duality between them.